In this poster we present the study carried out where we explore the potential of using alcohols as an alternative to hydrogen in fuel cells, focusing on cool glycerol as a promising option. The study involved synthesized gold-copper nanoalloys through chemical reduction, varying gold-copper ratios, and characterized them using ultraviolet-visible spectroscopy, scanning electron microscopy, and X-ray diffraction analysis. The UV-Vis spectra of gold-copper nanocubes shows an absorption band between 550 to 1 dozen nanometers. This behavior is attributed to the cubic morphology. The same characterization confirms the cubic shape of the nanoparticles and shows a size range distribution of 40 to 80 nanometers. X-ray diffraction indicates a face-centered cubic structure. And finally, the electrochemical profiles conducted in potassium hydroxide and a concentration of 2 molar showed that the nanoalloys exhibited zones corresponding to gold-copper. The nanoalloys demonstrated a good current density and selectivity for crude glycerol. These results indicate an optimal composition for the nanoalloys.
The synthesis of nanocubes was carried out using the following methodology. In a 20 ml vial, 10 microliters of 70 millimolar gold precursor salt and 10 microliters of 28 millimolar copper precursor salt are carefully dispensed. The vial is subsequently submerged in preheated silicon oil at temperature of 150 degrees Celsius to facilitate the complete evaporation of water. Following this process, 30 microliters of dodecanothiol are introduced and the temperature is then elevated to 180 degrees Celsius for 2 hours. After this period, the vial is removed from the oils and allowed to cool to room temperature, at which point 3 milliliters of chloroform are added. The resulting solution is subsequently subject to ultrasonic bath dispersion, culminating in a final characterized by a distinct grayish coloration.
Here are the results of products obtained during the synthesis. The UV-Vis spectrogram displays the absorption bands of both gold and copper at the same time. The characteristics of these bands are influenced by the relative presence of each component. For instance, in a 3:1 ratio, the 523 nanometers peak, which corresponds to gold, significantly broadens, while the peaks near 80, 870 and 990 nanometers are characteristic absorption peaks of copper. In a 1:1 ratio, both bands experience a decrease in intensity. Finally, in a 1:3 ratio, the absorption peaks of copper are more intense than the gold peak. In the scanning electron microscope image, panel A displays orderly arranged nanocubes measuring approximately 40 to 80 nanometers. Additionally, smaller spherical nanoparticles are visible on the surface of these cubes, along with a layer of orderly nanocubes beneath them. In the energy dispersive X-ray spectroscopy image, the analysis show that the gold-copper ratio of the analyzed nanocubes is 1:3. The elemental chemical mapping image indicates that the small spherical nanoparticles are composed of copper. The X-ray diffraction pattern displays diffraction peaks of the 1 through 3 gold-copper system. The peaks of the 1, 1, 1, 0 to 0, 0, 2, 2, and 1, 3, 1 planes can be seen at 2 theta degrees of 38, 44, 64, and 77 degrees respectively. These angles correspond to diffraction card code ID 901161-3 and indicate a face-centered cubic crystal structure, which is atypical of pure gold. The minimal presence of copper in the structure causes small lattice distortion, suggesting that they obtain nanocubes from a solid solution rather than in antimetallic material. According to the Scherer formula, the calculated size is approximately 50 nanometers. In the evaluation of the ultra-oxidation of crude glycerol, a 1 molar potassium hydroxide alkaline solution and 1 molar glycerol concentration were used. The potential window ranged from -0.9 to 0.9 millivolts and the scan rate was 50 millivolts per second. The voltammogram illustrated results from the first and 5 cycles, exhibiting a reduction peaks of 0.9 millivolts and 0.1 millivolts and 0.7 milliamperes at 0.1 millivolts respectively. Additionally, an oxidation peak of 0.01 milliamperes was observed in the first cycle at a potential close to -0.3 millivolts, and the 5th cycle this peak shifted to between 0.3 and 0.4 millivolts with concurrent of 0.1 milliamperes. This behavior indicates that the system is effective in reduction by products of crude glycerol oxidation such as carbon dioxide.
The conclusion for this work is that the exploration of multimetallic nanoparticles represents a promising approach due to their enhanced catalytic properties compared to single metal nanoparticles. This study has demonstrated the potential of using gold-copper nanoalloys as catalysts in the electrooxidation of crude glycerol as fuel in fuel cells, showing favorable electrochemical performance and structural characteristics. The result suggests that these nanoalloys with their optimal composition and catalytic properties could offer a viable and cost-effective alternative to traditional platinum-based catalysts, promoting the sustainability and efficiency of fuel cell technology.